Okay, so Greg Williams, the quasi-chemical model entropy term, because of the mathematics, is only exact when z equals 2. This gives you two sharp peaks here because you're only considering first nearest neighbors. You can keep z equals 2, which is physically kind of unreasonable, but mathematically gives you an entropy, which is pretty good. And add a Bragg-Williams term to make the thing rounder, or you can use z is greater than 2 and not put in a Bragg-Williams term, which makes the things rounder, but does have this problem of the entropy then becomes only approximate, and under certain cases you can have an entropy that's somewhat too negative. So we have done both in fact sage, and in present we are kind of mixing things up. So I said as in oxide systems we've always used, we started off using z as 2. For alloy systems we generally use z is equals 6 or 7 or 8. We often consider z to be since the whole entropy expression in the quasi-chemical model is approximate, mathematically approximate, we can treat z as a parameter of the model. That is, people have said, why don't you use z as 12 in an alloy, because you know that an alloy z is about 12, but it's a parameter of the model. You can pick the value of z you want in some cases just to make things fit better, okay? Because you're making up for this mathematical problem. Okay, just to show you a little bit about the z, why is the z, okay, well, I showed here that z, when z equals 2, I showed that if you had complete ordering when z is equal to 2, the thing comes in where it should, and when z equals 6 and higher it isn't. Okay, but to show that z equals 2 is an exact solution, you're not responsible for this, but if you look at number 19 here, this is actually first paper I ever wrote on the number 16. If you look at number 16, this is actually the first paper that Milt Lander and I wrote on the quasi-chemical model way back in 1984. If you look at page 287, I'm not going to go through all the details, but for those of you who like mathematical statistics, okay, here we have page 287, and I'm taking a yeah, it's this part here after between equations 20 and 21 on page 287 of number 16. How would we do? We're trying to get an entropy expression now in a one-dimensional lattice. And now we're going to, remember before we took XAA log XAA plus XBB log XBB, and then we made this approximation, and in order to make it come out right in an ideal solution, we divided XAA by XA squared and added the term in to make it come out right. Now let's do it correctly. Let's assume that we have a necklace of one-dimensional lattice. We say a necklace just so you don't have end effects. And we mix the A's and B's on the lattice. And now we have a certain number of A-B pairs. I'm doing this in terms of big N, which are the number of atoms. We have a certain number. Okay, sorry, here I use 1 and 2 instead of A and B, so let's call them 1 and 2, right? 1 and 2 are A and B. So we have a certain number of total number of 1s, we have a certain total number of 2s, we have a certain number of 1-1 pairs, we have a certain number of 1-2 pairs, and a certain number of 2-2 pairs. These are the atomic numbers. Okay, so we have a total number of N1 and N2, and we have N11, N12, and N22 pairs, and we want to mix these randomly in a one-dimensional lattice. Okay, so this is just mathematics here. You can read this through yourself and figure out, but how would you do this? This is now an exact statistical treatment, as opposed to the other, which was an approximate statistical treatment. What I do first of all, let's take the A's. First of all, I put all the 1s, I line up all the 1s. Okay? So I line up all the 1s. Now then, I figure out how many N12s I have. Well, I have a number of N1. I know I have N12, 1-2 pairs. So I put them randomly into the spaces here. I put it for the number of 1-2 pairs, I put a 2, I shove a 2 in here. I shove a 2 in here, this forms two N12 pairs. Now I form randomly, I pick another space between the 1s randomly, and I shove a 2 in here. And that gives me another couple of 1-2 pairs. Okay, so I randomly insert 2s between the 1s until I have a different one, not beside each other. I can't put okay, I choose the 1-2 space here, then I can't choose this space again. But I shove these 1-2s in between the atoms in order to give me the correct number of 1-2 pairs. Then the N2-2 pairs, I simply put in beside the 2s here in a number of ways. I have the 1, now 2, now I've got the right number of 1-2 pairs. Now I just move the 1 over and I put a bunch of 2s in here, randomly distributed with all these other 2s until I have the right number of N2-2 pairs. So you can read it and see what you're doing. But what it is you line up the 1-1, you line up all the 1s, you shove in the right number of 2s in order to give the right number of 1-2 pairs, and then you put the rest of the 2s in beside the 2s that are already there. That doesn't change the number of 1-2 pairs, but the 2s are then what you want. That's how it's done, but this is an exact statistical treatment. It's kind of very simple. You can just see this thing only takes a few lines. And that gives you an expression then that is exactly the same. When you work it out, you get an expression that is exactly what I wrote for the quasi-chemical model. But now it's an exact expression. Why then is it so hard to solve this thing in 2 and 3 dimensions? Is because in 2 and 3 dimensions you can't shove atoms in between other atoms. So what I can do here is I can line up all the 1s, and every time I shove a 2 in, I form a 1-2 bond, and the lattice just expands. But now if I have a 2-dimensional lattice, so let's try to do the same thing with a 2-dimensional lattice. First of all, I put all the 1s on the lattice sites. Now I try to shove in 2s in order to form the 1-2 bond, but you can't like shove a 2 in here, because then this moves over, and you can't do it in 2 and 3 dimensions. You can't insert things so simply just to expanding your lattice, and the whole thing becomes extremely complicated the minute you go beyond 1 dimension. Okay, so the exact solution in 2 and 3 dimensions is beyond what we can do, but in the 1 dimension, the whole thing, and interestingly enough, the 1-dimensional, when you do the 1-dimensional right, you end up getting exactly the same expression as I showed you, xa over xa squared plus xbb log xbb over a. You get exactly that expression. So you can follow the thing. This, by the way, this model that I wrote, the quasi-chemical expression for the entropy, is called the Ising model. After a Belgian, actually, who developed it in the 1930s, named Ising. He didn't develop for quasi-chemical, he developed it to actually talk about magnetism, where you have the spins aligned and unaligned, and it's there you have a number of, in a 1-1 in a lattice, you can have your spins of the atoms aligned or unaligned as you go along. And if the spins are aligned or unaligned, if the spins are aligned, you get a negative contribution that gives energy, and this is why you get ferromagnetism. And so he was trying to, it's the same sort of model, you're trying to model distribute the number of up, up, down, down, and down, up pairs among the sites of the lattice sites. Later on, we developed it into the quasi-chemical model. It's the Ising model term for the entropy. Okay, so if you want to read that, you can prove to yourself you're not responsible for it, but you can see it's really very simple to do the exact expression in 1 dimension. Now if you go back to, did I get that up? Oh, I keep doing that. All right, continue on here. So now okay, so the development up until now, the minimum always comes at 50% because you have AB bonds. Now we've determined in many cases, however, that you have a minimum that is not at 50% if you take the aluminum calcium system. If we take the system's aluminum calcium, for example, experimentally we find the heat of mixing has a sharp minimum around the composition Al2Ca, and the entropy similarly has a minimum around that same composition. Now, if you're going to do this in the associate model, then it's very simple. You simply write the associates not ALCA but AL2CA. Okay, so in the associate model, then you have your single lattice, and on the lattice you can have an A or B, or you can have an A2B, associate. There is a problem with this too, that as X calcium approaches 1, it doesn't obey Reynolds' law. Reynolds' law, as X calcium approaches 1, if you have a very rich solution in calcium, say in B, which is now calcium, in reality when you add, you notice when you add A, experimentally, if you start with calcium and you add A, it obeys Reynolds' law. Every aluminum is going in as an independent particle. But now the aluminums, if this is very strong, the aluminums, two aluminums are doubling up to form Al2. So you only get half the entropy. So you only get half the limiting slope of your liquidus. Your limiting thermodynamics doesn't obey Reynolds' law properly. That's the problem. Maybe not too big a problem, but it's a problem. In the quasi-chemical model, now how do we go about it? In the quasi-chemical model, we change the coordination number. We let the coordination number of calcium be twice the coordination number of aluminum. And we assume for the moment that these are constant with composition across the whole system. Now our mass balance, so what that means is that if you're at the, for example now if you're at this composition Al2Ca, and let's say the omega is very negative, in that case what you'll have here is you'll have a lattice in which the aluminums are surrounded by calcium and the calciums are surrounded by aluminums, and the coordination number of calcium is twice that of aluminum. So every calcium might have 12 aluminums around it, every aluminum has 6 calciums around it, like a crystal structure, like CaF2 crystal structure, for example. In crystal structure of calcium fluoride, you have twice the coordination. Calcium has twice the coordination number of fluorine, so you can imagine a local crystal structure. Now this can change, this you cannot do in a solid solution. In a solid solution, it has you have a structure. You have one phase, you have the single structure, so the coordination number can't be changing. But this is possible in a liquid. In a liquid, the coordination number can vary as you move across the system. So calcium and aluminum can be completely miscible in the liquid state, and the coordination number changes as you move. This is the local coordination number. So the local coordination number around a calcium can be different from the local coordination number around aluminum because you don't have a rigid lattice. If you're dealing with a solid where you have a rigid lattice, then you can't do this. Okay. You're replacing aluminums by calcium in a rigid lattice. The calciums have to have the same coordination number as the aluminum that they're replacing. But this is possible in a liquid. The mass balances then work out this way. ZAXA is the number of bonds around a central A. ZA is the coordination number of A. ZA then is the coordination number is the number of first nearest neighbors. So the number of first nearest neighbors around a central A atom is ZAXA, and the number of around a central B atom is this. In the few slides before, these Z's were the same, now they can be different. And now Reynolds' law is obeyed as X calcium approaches 1 because you're not adding molecules, you're just adding. All right, so that's how so we just have a new quasi-chemical mass balance. I didn't show this here, but what's going to happen say we have a heat of mixing AB and we have A2B, and so we have ZB equals 2ZA. So what's going to happen now when omega is very negative? Omega is very negative, you're going to get the heat of mixing. It's going to have a peak, very sharp peak. And the peak's going to be very close to the A2B composition, because that's at A2B composition, all A's are surrounded by B's, virtually all B's are surrounded by A's. If omega is very negative, then it's very strong ordering. And similarly, the entropy expression also is going to come down like this and be ordered around the A2B composition. But now as omega becomes less negative, the thing tends back towards an ideal solution. Okay, and then that in the limit, as omega becomes larger, as omega becomes less and less negative, the heat of mixing will become less negative, the entropy will become less peak, but also the peak will now move back towards 50%, because if you reach the limit where omega is very small, the system is almost ideally mixed, so it's almost a regular solution. Okay, so what happens is as omega becomes less negative, the peak becomes less sharp, but at the same time, the minimum point moves over towards 0.5. And similarly here, as omega becomes less negative, the peak becomes less thing, but it moves over, so that once you get back to when you get the ideal limit of the entropy, the minimum is at 50%. So the ideal limit where omega equals 0, you have an ideal entropy, and you have the minimum at 50, the maximum, and the entropy is at 50%. As you then make omega more and more negative, you get this M shape, and this minimum point will move over towards the A2B. Okay, so I've seen people who had the quasi-chemical model. They said, well, I let Z be 2Z, why don't I get my minimum at 33%? Well, you will get your minimum at 33 1/3% if your omega is very negative and you have extremely strong ordering. But as it becomes less ordered, so your minimum is the actual minimum that you get from the model is going to be somewhere in between the 2-to-1 and the 1-to-1 ratio. I missed mentioning something that is one of the main features, this is very easy to show too, of the quasi-chemical model. Let's go way back to the quasi-chemical model. The quasi-chemical model, when omega is very negative, okay, so when omega is very negative, the quasi-chemical model gives you this U shape. When omega equals 0, the quasi-chemical model reduces to the ideal solution, which is what you expect, what you want, which the associate model doesn't. But there's another thing, that if omega is small, not 0 but small, if omega is 0, is not 0 but it's small, then the entropy, then the model reduces to the regular solution model. Because as omega becomes small, the configurational entropy becomes very close to ideal. And now the heat of mixing, okay, so as omega not equals 0, but omega is small, either positive or negative, delta S configurational is approximately equal to delta S ideal. The smaller is omega, the closer you get to the ideal mixing, simply because this thing moves back to the right. The entropy always wants to go that way. Okay, and the heat of mixing in the quasi-chemical model is given by XAB over 2 times omega. But when omega is small, the distribution is roughly random, and so XAB is approximately equal to 2XAXB. The probability of an AB pairs is 2XAXB. Shoving this into here, we get delta H is XAXB times omega, which is the regular solution model. Okay, so when omega is equal to 0, the quasi-chemical model is ideal. When omega is small, the quasi-chemical model reduces to the regular solution model. And the parameter is even numerically the same as the regular solution model. That's why I put the 2 in here. No other reason than I would like it to come out to this. I don't have to put the 2 in, but then the omega is twice the other omega. I prefer to have it this way. And if, as you know, we're going on later on, the omega now doesn't have to be constant. The omega quasi-chemical doesn't have to be constant. It can be a polynomial in the mole fractions. And in that case, this reduces to the polynomial model, what we just talked about. So then the question would be, well, why then ever use the polynomial model? Why not just always use the quasi-chemical model? Because the polynomial model is actually, the regular solution model says that you have ideal entropy, but your heat isn't ideal, but this can't be right, because if your heat isn't ideal, heat isn't 0, then you won't have exactly the proper configurational entropy. The quasi-chemical model corrects for that. So actually, there's really no reason, even if the omega is very small and the solution is almost ideal, there's no reason not to use the quasi-chemical model. It gives you a little bit better entropy expression. As omega becomes, as delta H becomes more and more negative, the configurational entropy has to deviate somewhat from the ideal. So the regular solution model is not a different model. The regular solution model is just a case of the quasi-chemical model in which we have forced the configurational entropy to be ideal. But I mean, this isn't really right. So there's really no reason not to use the quasi-chemical model, even for small values of omega. Even when the distribution is close to random, you might as well take into account the fact that it isn't exactly random. But of course, the mathematics is a lot simpler in the polynomial model. So if it really is roughly random mixing, you can use the polynomial model. But there's absolutely a Bragg-Williams model. But there's really no reason to use the Bragg-Williams model over the quasi-chemical, except that the mathematics become simpler. But then if the computer's doing the mathematics for you, what difference does it make? All right. Prediction of ternary properties from binary parameters. So how well does the quasi-chemical model then predict the ternary properties from the binary parameters? Because this is really what we're trying to do. Well, we're trying to do two things in our optimizations. We're trying to get nice databases for the binary solutions, and in that you can see that for a binary solution, which is quite well ordered, that where the omega is quite negative, really the quasi-chemical and the associate model give you almost the same fits. You get very, very similar fits to the binaries. Now, that's, however, the quasi-chemical model also is good around systems that are not highly ordered, when omega is small, or even when omega is positive, whereas the associate model is only good for systems that are highly ordered, because it does not reduce to the ideal solution model. But even for systems that are highly strong, with a lot of strong range order, and even though the binary solutions are fitted almost identically with the quasi-chemical model and the associate model, you'll find they get very different approximations when you go into the ternary systems. Okay, so let's look at the example, aluminum, scandium, magnesium. Magnesium and aluminum magnesium are lesser. The aluminum scandium is the system that has the strongest short-range ordering. So in this system here, aluminum, scandium, magnesium, we'll have aluminum, I don't know how, scandium, I think that's the way I did it, magnesium. This system has a strong short-range ordering in it. The scandium and aluminum want to be next to each other. The other two binary systems here are not very much ordering. Now, this is then, okay, I did it the other way around here, so let's do it this one. And this is very typical now of this type of solution. The phase diagram, this is the Liquidus projection. Okay, so you look at this system, this is the Liquidus projection. Here it's calculated, but this is what the measure looks like. So these two systems are quite ideal, and this system is quite negative with a very strong ordering. And what you see is these are the Liquidus curves of different compounds that are in this aluminum scandium system. And you can see they're very, very flat. These are isotherms, of course. The isotherms are very widely spaced. If the isotherms are widely spaced, it means you go a long distance in composition before you get, as you lower the temperature. And these are, you see that these strong, so this is positive deviation. I mean, widely spaced Liquiduses means the Liquidus is up, so this is a positive deviation. If we treated this system here in the liquid phase, if we treated this system here as an ideal solution, okay, these isotherms would be much closer together, the Liquidus would be much, much lower. If you started here and you went down, if you went across this way, you'd be descending in temperature much, much more quickly. So this is very typical. So again, this seems a little bit backwards. Here you've got aluminum, there's very negative deviations here, forming the associate, not associates, but the nearest neighbors, short-range ordering, and yet this gives you positive deviations, aiming from this corner up towards the ordered side. This will give, the Bragg-Williams model will also give you this. Let's take the Bragg-Williams model. So I have, this is the Bragg-Williams model. Delta H is XAXB times omega Bragg-Williams in the AB, so on. So this is your regular solution with the Bragg-Williams model, random mixing. Let's didn't come out in the slide. This should be very negative. So omega AB is very negative, while the other ones are roughly 0. So here we have A, B, C. Here we have omega is approximately 0. Omega over here is approximately 0. And over here we have omega is very negative, which is going to give you negative deviations over here. Maybe not the nice sharp peak you want, but at least negative deviations on this side, right? Now, about an hour ago, I wrote this out and I said, why, when you have a negative deviation here, when this is negative, then you can get a positive deviation for the other thing? It's the same thing here. What's happening is you add, if you take, say, your ordered solution over here, aluminum scandium, and you add magnesium to it, what you're doing is you're diluting it, okay, and therefore you're breaking up these very strong magnesium AB bonds are being broken up by the fact they're being diluted. So this gives you a positive contribution. And that's why you get a positive deviation along here. Or in other words, A and B want to be together, nearest neighbors. They don't want to be next to C. In the Bragg-Williams model, you're forcing them to be next to C because you're saying it's a random mixture. Okay, so as you add magnesium, you're getting a positive effect. Okay, the A and B want to stay together. They don't want to be next to C. What they'd like to do is they would like to form clusters of AB and let the C be over here. In the Bragg-Williams model, you're forcing the C to go in because you're saying it's a random mixture. Okay, so every time you add a C, you're breaking up these strong AB bonds. So this gives you positive deviations along this line. Okay. So positive deviations result along the ABC join, and the Bragg-Williams model, however, overestimates these deviations because it neglects the short-range order. So this is a liquidus line. This is the temperature versus composition along the line Al2SC to magnesium. Okay, so we're going Al2SC is around here, and we're going along this line. Okay, so this is actually it's very close to a quasi-binary section, but it's an isopleth going from Al2SC, which is here, along to here, temperature versus composition. So you can see this very widely spaced isotherms are basically very flat liquidus. You go a long way in composition before you drop in temperature. Okay, so this is just the solid line is these experimental points. Are they clear how this relates to? Okay, so if this was an ideal mixture, then the liquidus would come down like this. You have these positive deviations because of the effect I just talked about. When you do the Bragg-Williams model, what we did, the Bragg-Williams model, then we fitted up all 3 binary systems using the Bragg-Williams model. You can't get a really nice fit here because you're not taking into account the sharp peaks, but still you get a reasonable fit. And this is what you calculate with the Bragg-Williams model. Not only do you get this, remember way back we said a flat liquidus is a tendency to demixing. In this case, the Bragg-Williams model, the whole thing actually demixes into 2 liquid phases. It overestimates. Okay, it gets the effect, qualitatively it gets the effect right. Along this line from Al2SC to magnesium, you should get positive deviations. And in fact, it gives you positive deviations, but they're way too big. And the reason they're too big is what I said. In the Bragg-Williams model, you're forcing the entropy to be ideal, randomly mixed. So the magnesium is going in whether it likes it or not. It's going in randomly between the aluminum and the scandium, and it's breaking them up. In reality, if you took into account short-range ordering, okay, then the aluminum and scandium can keep together and exclude the magnesium. You could increase the number of aluminum-scandium bonds. They don't have to be randomly mixed. Okay, they can form clusters. And that will then permit the system to... The system is always trying to lower its free energy. It doesn't want to have a positive free energy if it doesn't have to. You're forcing it by putting a physical restriction on it that isn't really there. By forcing it to be random, you're forcing it to be more positive than it would like to be. If you remove that restriction and you let the aluminum and scandium get next to each other, then you can lower the... And now here is then where the whole thing, this is where the associate model is no damn good. Because the associate model does not account for positive deviations along here at all. In the associate model, what have you got? In the associate model, remember, you've got a lattice with A's, B's, and A2B's. NCs. Okay, so over here you got Al2SC molecules, and over here you've got magnesium atoms, and you're just mixing them randomly along this line. There's no, this business of the magnesium breaking up the aluminum scandium isn't there. The magnesium doesn't break up the aluminum scandium because they're molecules. Here's your aluminum scandium, they're molecules. You add magnesium, you're not busting these things up. What you get is you get simply an ideal solution along here, which is not at all what is observed. Okay, this is the associate model, gives you way down here. No positive deviations whatsoever. And this is why whenever you see systems like this, when people fit up systems like this, you look at this, you just look at this, and this tells you that you have ordering here, and this is trying to find positive deviations. If you fit this system up using the associate model, you get a beautiful fit in the binary system, because as I said, in binary systems, the associate model, if it's negative omega, is very, very close to the quasi-chemical model mathematically, but you won't get this at all as you go into the ternary system. And what you're then obliged to do is you're obliged to add ternary parameters to bring your Liquidus up, and this is totally artificial. So the associate model has no predictive ability. Okay, it might fit up the binaries nicely, but in the ternary it's very, very different from what you actually observe. You're always then having to put in these ternary parameters with your associate model. Now, going back here then, if you used your associate model, you're going to get you're not going to get any positive deviations. Way too low on Liquidus. If you do Bragg-Williams, you go the other way. You get your positive deviations because the magnesium is busting up the aluminum scandium, but it's overdoing it. The quasi-chemical model is just right, like Goldilocks. Okay? Because it comes in between. It doesn't have the associates. As you add magnesium, you do in fact break up the aluminum scandium pairs. But since you're permitting short-range ordering, the aluminum scandium can get together, so you're halfway in between. And you can get the right answer if, of course, you choose the right value of Z and the right value of the Bragg-Williams quasi-chemical model. Okay. So here we use Z equals 6. If we use the quasi-chemical model with Z equals 6 with no Bragg-Williams term, then this is what we predict. And this is with no ternary terms at all. So positive deviations, but not too much. This, if nothing else, is the main reason to stay away from the associate model, because it can never give you proper things in a multi-component system. So taking short-range order into account with the associate model makes things worse. Now the positive deviations are not predicted at all. Along this join, the model predicts a random mixture of A, B, and C's. The quasi-chemical model gives you correct predictions, but these of course depend upon the ratio, omega Bragg-Williams or omega quasi-chemical, if you want to do it that way, with Z equals 2, or the other way of doing it, if you don't put any Bragg-Williams terms in, then what value of Z do you choose? Okay. So I'm calculating along this line here, these are liquid-liquid miscibility gaps. I haven't put in any solid. This is a hypothetical system. No solid phase. So this phase over here, this system over here has strong ordering around AB, and these two systems over here are ideal. And so I'm going along the line from AB to C, and the phase diagram. I just put the liquid in here, but this is two liquids. So this miscibility gap, as the positive deviations get bigger and bigger, you get a higher and higher miscibility gap. So these are then predicted fitting up the binary systems. This using minus 40 kilojoules per mole for the quasi-chemical parameter here and 0 over here. You find that with, well, this is the Bragg-Williams quasi-chemical. If you take the just the quasi-chemical model along this line with omega, so Bragg-Williams over omega quasi-chemical is 0.5, 1, 2, 4, 8, and here you have the Bragg-Williams limit. You see that, as you expect, the miscibility gap is large for large when you have just Bragg-Williams, and it gets smaller and smaller when you introduce the quasi-chemical model, which is the same thing as saying here. The Bragg-Williams gives you a high, very high, too big a positive deviation, The quasi-chemical model with Z is 6 gives you the right answer. If I took the half and half Bragg-Williams quasi-chemical, I would probably get a miscibility gap, but it would be smaller and smaller as I change the Bragg-Williams quasi-chemical ratio. So the bigger the Bragg-Williams term, the bigger is your miscibility gap. So I said there's two ways of doing it. One way of doing the quasi-chemical model is to let Z equal 2 and put in Bragg-Williams terms to make it bigger or smaller. The other way is to just change the value of Z, keeping no Bragg-Williams term, just keeping a value of Z, and it's the same thing as you would expect. Small values of Z give you a smaller gap, and bigger values of Z make it more closer towards the Bragg-Williams model. And you will notice something here that I have not put in, purposefully I did not put in Z equals 2. And here I did not put in just Bragg-Williams either, where Z is 2. Z is 2, I put in some Bragg-Williams, and that's because if you take the quasi-chemical model with Z equals 2 and no Bragg-Williams terms, you don't get a miscibility gap along here. You get a very flat liquidus, but you will never get a miscibility gap. Now let me explain why that is. Okay. So it doesn't mean with Z equals 2. With Z equals 2 and no Bragg-Williams term, let's go back to here. If I were to put in this with Z equals 6, with Z equals 2 you expect to be a bit lower, but it's not much lower. With Z equals 6 you get this. As you increase Z, 12, 20 and so on, it goes up. When Z's infinity you're back to the Bragg-Williams limit. If you take the lower than you go to Z is 2, you get something that's down like this. Okay, it's going to be a little bit lower, so Z is 6 was better. Z is 2 is down here, but now suppose I took Z as 2 and I just made the omega parameter more and more negative. This would move up, but it would never ever give me two liquids. It would come up to a perfectly flat liquidus, horizontal, but I would never actually get phase separation. I'll explain to you why that is as well. That's another problem with your Z equals 2 with no Bragg-Williams term. Okay, anyway, this is the predictive ability. So what do we do in fact stage? So do you choose Z equals 6? This is part of the reason that we have fixed a certain values of Z. And many of our alloys and so on, from experience, we have found that if we're not using the Bragg-Williams term, setting Z around 6 gives you a really good fits in most systems, alloy systems. So that's why we stick with Z equals 6. But it is actually a parameter of the model. You can fiddle around with it. But we've just found that if you let Z equal 6, it gives you just about the right sort of thing with the along here, at least in the alloy systems. The trouble is in the oxide system, since we've used Z equals 2, you don't get any miscibility gaps. You have these, but if you take something like the calcia silica FeO system, this is highly short-range order. This is also short-range order, but not so much. So along this line, you're getting these positive deviations with your liquidus curves that come out like this. And we're using Z as 2, we can reproduce that pretty well. Okay, but were the system a little bit more negative over here, and you actually had a miscibility gap, we would never get it. We couldn't reproduce it with the Z equals 2. If you put in Bragg-Williams terms, you can. If you put in Z greater than 2, you can, but not with just Z equals 2 and no Bragg-Williams terms. I'll explain in a minute why that's the case. This is something that we've had a lot of arguments about. John Kahn and Ising abandoned science because of it. Okay, so for the moment anyway, let's just go back to what I'm trying to show here, is that why you get positive deviations along that line is very important. There's many systems are this way. They have this type of thing. Here I've assumed this is more or less ideal, but I mean, even if this is less, what you have is one system that is more negative deviations, more order than the other, you're always going to get this kind of thing, and this is a major effect. Okay, this is not trivial. This is your difference between your associate model and your quasi. I mean, you're talking about hundreds of degrees here. It's not a small thing. This is a major thing. If you try to use an associate model, you're going to have to put in big ternary parameters, positive ternary parameters, in order to force the thing to fit. If you use the Bragg-Williams model, you're going to have to put in big negative ternary parameters to force the thing to fit. And this is because the models just are not reflecting physical reality. You can fit up a binary system not too badly, sometimes with models that are not physically realistic. So this aluminum scandium system has as I showed, if you have a binary system with negative deviations, you can fit it up the binary almost the same with the quasi-chemical model and the associate model. Okay, but that's because the mathematics in the binary are very similar. When you go into the ternary system, and now it has to be, you're really basing it upon chemistry, what's really happening. The associate model falls down because what's really happening is not that you have Al2SC molecules. Okay? You're having the nearest neighbor pair. Okay. And I think it's important to understand the difference. The associate model, the magnesium does not break up the aluminum scandium complexes. In the Bragg-Williams model, it breaks them up, but it overdoes it because you don't allow them to cluster. In the quasi-chemical model, it breaks them up, but not too much because they can cluster. Alright. So far, I've talked only about binary systems with, maybe I should, okay, while I'm on that, you can look at I just did a little mathematics here, which you could look at home. This is number 19. Just to actually do the mathematics along that line. So I've got a, if you like to do the mathematics, what I just talked about is in words, but let's actually take the system A, B, C, go along this line, calculate the Gibbs energy, using the Bragg-Williams model to show you get positive deviations. I mean, you can see why you get positive deviations. As I said, as you add C, here you have your complexes AB. Here you have an A1/2, B1/2. You have not complexes because you're using the Bragg-Williams model, but you have a very negative. Along here you have omega AB is negative. So you add C, you're breaking up the AB pairs. Okay, so that's why you get the positive deviations, but let's actually do the mathematics. Okay, so here I have the system A, B, C, and on this sheet number 19, I assume this is an ideal solution, I assume this is an ideal solution, and I assume this solution is Bragg-Williams, that is XA, XB, omega, with a negative omega. Clearly around 50%, so what you're going to do is along this line here, you're going to get positive deviations, and you can get a miscibility gap. This is a miscibility gap centered on this line. Okay, so let's look at the line going from A1/2, B1/2 to C. I do it this way so you got 1 mole total. And along this binary line here, so what, this is Bragg-Williams, so I should write here. Okay, omega AC equals omega BC equals 0, and omega AB is quite negative. And they're all constant, so it's Bragg-Williams. Alright, so I go along this, so I'm drawing G excess now going along that line. So this is the excess Gibbs energy going from here to here. I place this end at 0 at A1/2, B1/2, and I just calculate the excess Gibbs energy along that line. Along that line, I'm considering quasi-binary coordinates, so this is mole fraction of C and there's mole fraction of A1/2, B1/2. So it doesn't mean that there's a particle A1/2, B1/2, this is just formally. The mole fraction of A1/2, B1/2 is 1 minus the mole fraction of C along there, which is equal to XA plus XB, where XA equals XB along that line. Okay, so now I'm considering this reaction where I mix A1/2, B1/2, so I'm taking a solution at that composition already mixed, and I'm mixing it with C. So I'm considering this reaction of taking this solution of 1 mole of solution at this point, already mixed, and mixing it with C. So XA 1/2, B 1/2 moles of this already mixed solution plus XC times C forms my solution. The excess Gibbs energy for that is the excess Gibbs energy with respect to A, B, and C minus 1 minus XC times the excess Gibbs energy at that point. It depends what you're referring it to. Okay, I'm mixing these two. So at this point, you already have an excess Gibbs energy in the binary system, AB. Okay, so I mean, this graph, if this were GXS in the entire relative to A, B, and C, then this curve wouldn't go to 0 here, it would go to some point up here, which is the excess Gibbs energy in that system. Okay, so I mean, this is I'm just reducing it. This would be GXS along the line A 1/2, B 1/2, C. If this is the GXS with respect to A, B, and C, then the curve would look like that. I'm making it with respect to this point down here, so the GXS here is equal to the GXS here minus this times 1 minus XC. So this is the Gibbs energy in the ternary system is omega XAXB minus then the excess Gibbs energy in the binary system at 1/2 times 1 minus XC. Think about it, and you end up with an omega. You end up with the GXS along that line is minus omega over 4 XC times 1 minus. It's a regular solution. XC times 1 minus XC times minus omega over 4. So if omega is negative, GXS along that line relative to these two starting points is positive. The reason is, as I said, you're adding the C, you're breaking up these nice bonds that want to be together that are negative. So if you like the mathematics, there's the mathematics to prove it. It's actually a regular solution along there. But throw it over 4. I would like to show you then the number, just to show you how this can work quite nicely. (14A). This is a paper we wrote recently. Magnesium aluminum tin system. And in that system, it's similar to the scandium aluminum magnesium system. You have one system which is okay, so the magnesium tin solutions are quite strongly ordered. You can see the sharp peak around Mg2Sn. And you see this S-shaped excess Gibbs energy, which also explains it. And if you look along here, Mg2Sn over towards aluminum, you tend to have these positive deviations. This is your line along which you're getting the positive deviations. This is your main short range order is over on this side. Around here, it's tin aluminum and magnesium aluminum are much less ordered. Okay, so once again, it's like the aluminum scandium magnesium. You have your widely spaced liquiduses and you're going along this direction. Okay, so we applied the quasi-chemical model to all three binaries. And that is the prediction, the phase diagram along this line, calculated and measured points. Similarly, we're fitting the heats of mixing. That's along another line. These are along different sections. These are experimental and calculated points along various sections of the diagram. You can look this paper over. These are other sections. And this is with no ternary parameters. This has also been optimized by the Germans using the associate model, but then they required ternary parameters. They needed the ternary data, fitting it Now, of course, here we've chosen the Bragg-Williams quasi-chemical ratio, but you can read the paper. But in these sort of systems, that's just showing that you get quantitative agreement. You can fit most of these things up with very few. In this case, with no ternary parameters, you're getting fits that are within the experimental error limits with everything. This is the enthalpy of mixing. This was the aluminum scandium system I showed you before. We do a little bit more in that system now, and there are fewer data, but we're reproducing that one as well. This is the... Okay, so if you want to look at that to see the actual... This shows a whole lot of numbers, and you'll see how we do it. But that's the archetypical example, but it's like, I admit that's better than we usually get. But we're getting like a really good fits using this thing, and I think this definitely shows what's going on. You can't get that with the associate model, nowhere close. And you certainly can't get it with the Bragg-Williams model. That goes too far the other way. Okay, I'm going to leave the positive deviations for tomorrow, but I can do just one more quick thing today. Okay, if you have, okay, I showed you that with Z, we did the, yeah, 14 on there. How do I keep losing these things? All right, this is the last thing I want to show you. Okay, earlier on today, I showed you that this, I wanted to show that the entropy, you have the entropy, when you have the quasi-chemical model, you want the quasi-chemical model is very negative, and you want it at 50%, you want the entropy to go to 0. Okay, so I said that this, again, put Z or 2 in here, and then I substituted in the values here with Z as 2, and I showed that in this expression, when you choose Z as 2, and omega is very, very negative, when xa is equal to xb is equal to 1/2, xa is equal to 0, you substitute in and you get that expression. Okay, and that, fine. That was for the case, however, where there was a constant z. Za and zb were the same. What happens now if you take the z to be different? Let's say you have Z calcium equals 2Z aluminum. Okay, now what value of Z? What I do now, so now you're going to get a minimum here at the composition Al2Ca. Okay, so what I want to do is the same thing. I want omega to be very, very negative, or omega equals minus infinity, so you have extremely strong complexing. At this point then, you're going to have only Al-Ca bonds. So now I want X aluminum to be 2/3. I want X calcium to be 1/3. And at that point, X aluminum equals X calcium equals 0. And X aluminum calcium equals 1. And I want to substitute that into this equation, but now I have two different Z's. I have a different mass balance here. Okay, and how am I going to get, what value of ZA and ZB do I have to choose in order to make the entropy go to 0 here? Okay, if ZA equals ZB, the minimum's at 50%, and it's easy to show that the Z has to be equal to 2. If I, again, remember, I'm dealing with an entropy expression which is not mathematically exact. I want the minimum to be at 1/3 here. What values of Z do I have to choose? And this is just pure mathematics, nothing to do with anything scientifically, but this is what we would like to happen. So you can look at this and see. And then I lost it again. This was this number 19, no, 16 again. Page 288, 289. This is the old paper, so our notation was slightly different. But you can follow it through. I just did basically the same thing. You write out the expression for the entropy, and you find that you get when A is 0.69, and so when you end up with ZA is 0.69, and ZB is 2 times 0.69. You end up with the minimum at that point there. And this is just pure mathematics. So when you go back, when you look in the FactSage database, I said the FactSage database for the oxides, if you take calcium-silica, I said for the oxides we've always used Z as 2, but this isn't quite right. What I meant was in the oxide systems we always chose a value of Z, so that for infinitely negative omega you would get the entropy going to 0. In that case you've got to fiddle it around. This averages out to 2. But one side is a bit less than 2, the other side's a bit more. Actually, sorry, ZA is that times 2. It's 2 times that. So this would be 4 times that. So ZA would then be 1.38, and ZB will be 2 times 1.38. So you end up with the Z that's it's not exactly an average of 2, but the ZA is less than 2, the ZB is greater than 2. There's a little formula here which will show you exactly how to do it. We can talk about that on Thursday. Okay, but you see the idea here is I'm simply putting it back into the expression and finding what values of ZA and ZB will shift this over but still keep it 0. So one's got to be a bit less than 2, the other's got to be a bit greater than 2, and that fits it in. So if you look in the FactSage database for, say, calcium-silica, the minimum here is at Ca2Si, or whatever. Okay, and you'll find that the Z of calcium oxide is 1.38, and you'll find that the Z of silica is 2 times 1.38. And that's the reason. This is, of course, purely non-physical. Coordination numbers, of course, can't be fractions, but it doesn't matter. That's why we did it. I probably wouldn't do it that way now, but that's the way we did it then. I'll show you those, but you can read that over if you want.
Let me see how it looks like.
Okay, so on Thursday I'm going to continue with the showing the short-range ordering quasi-chemical model when you have positive deviations, when you get actual positive deviations in binary systems, which give you miscibility gaps. And then I will go to the paper, then we'll do the whole thing rigorously. This was a somewhat non-rigorous way of doing it, just to give you the idea of what physically is going on. Then I will be talking on Thursday, when I finish this up quickly, then I'll be going on to this number 17 here, which is the modified quasi-chemical model, paper number 1 and paper number 2, which were the papers where we gave everything about it, and using the modern notation as well, the notation that we're still using today. This paper here that I just showed where you have the Z1, Z2, this was using an older notation, although it's the same equation. So if you want to prepare for Thursday, you might look at number 17 here. Get over. Okay, but there's nothing in 17, it's just the quasi-chemical model with all the bells and whistles and the proper notation. Okay, there is one. Okay, for the remaining course, it's 2 days I have to be away. This is Tuesday, November 8th, I won't be here. I have to go to a meeting. Also, I'll be at the meeting on November 9th, Wednesday as well. You people said you have Wednesdays free if I need to shift it, but unfortunately, Wednesday, November 9th is also, I'm away. So I'm thinking of replacing this by Wednesday, November 2nd. In other words, the week of November 2nd we'll have 3 courses, Tuesday, Wednesday, and Thursday, and then the next week we'll only have 1 course on Thursday. Is that okay? Okay, so what time do you want to come on Wednesday, November 2nd? Prefer the afternoon or the morning? Actually, it has to be the morning, because there's a possible thing in the AM, so this has to be at 10 o'clock. Okay. Okay, so we'll have Wednesday, November 2nd at 10 o'clock. Or we could even do that sooner. You want to make it, is 9:30 okay? Let's make it 9:30 Wednesday, November 2nd. Instead of Tuesday, November 8th will be canceled. Also, the week after this, Thursday, November 16th, I can't make it, but I am free Wednesday of that week, so this could be Wednesday, November 15th. Sorry, 16th, oh, sorry. This is, sorry, 17th is on. We replace that by Wednesday the 16th. Is that right? The 8th is a Tuesday, I hope. Yeah. Wednesday, November 16th, and there we can also have it. So can we do that then? Tuesday, November 8th replaced by Wednesday, November 2nd at 9:30. Thursday, November 17th replaced by the November 16th.